Hey guys, welcome back to my channel. In the part 1 for the dynamic programming video I made, I got some comments on where to get resources on dynamic programming. You can always check out leetcode.com, click on the explore page, and then you will find the dynamic programming card amongst other cards. You can always go there to learn more about dynamic programming. Hi guys, welcome back to my channel. So this is a continuation of the dynamic programming series. In the first series we solved the Fibonacci sequence using dynamic programming. So in this second series, the second part, we're going to be solving this problem which says that a grid traveler travels on a 2D grid, begins his journey on the top left corner, and his goal is to travel to the bottom right corner of the grid. In how many ways can he travel to the goal on a grid with dimensions m by n? Note, he can only move to the right and to the bottom of the grid. He can't move left and he can't move up. So our input is going to be two integer values, which is going to represent the dimensions of the grid. So this is going to be m by n. So we're going to have two inputs. One is going to be m, which is an integer, and the second one is going to be an m, which is an integer. So m is going to represent the number of rows and n is going to represent the number of columns. And the output is going to be an integer, which is also going to represent the number of ways that the traveler can take to get to his goal or his destination. So for us to understand this question faster, I'm going to illustrate it on a grid or a matrix. So let's see. Okay, here. So here we have this 3 by 3 grid, and the traveler starts from position 1 by 1 and ends at position, and the end goal is position 3 by 3. So all of these represents the positions of each grid. So the first one is row 1 column 1 position, row 1 column 2 position, row 1 column 3 position. So now the traveler wants to travel from row 1 column 1 position to row 3 column 3 position. So in how many ways can he achieve this? So looking at this grid, we can see that he can travel to this position by 6 ways, or in 6 ways. So let's see. He can take this route, which is 1. He can take this route, which is 2. He can take this route, which is 3. He can also take take this route. He can take this route, which is 4. He can take this route, which is 5, and he can take this route, which is 6. So we can see that on a 3 by 3 grid, the traveler has 6 ways to get his destination. So let's assume that this is going to be a 2 by 3 grid. That's 2 rows and 3 columns. So let's just use this marker to just represent this part. So this part is not part of it. So we just have the 2 by 3 grid. So the traveler starts from here, and this is the end goal here. So a 2 by 3 grid is going to have 3 ways to travel. So he's going to either go this way, or he's going to either go this way, or he's going to go this way. So this is 3 ways to travel on a 2 by 3 grid. Now let's try to illustrate this thing on a tree. Now if you have a 3 by 3 grid, so the traveler can either go down or he can go left, he can go right. So he can't go left and he can't go upward. So this represents down movement and this represents right movement here. So on a 3 by 3 grid, if the traveler goes to the bottom, so he has two rows and 3 columns to navigate. He has 2 by 3 grid to navigate, and if he goes to the right, he has 3 by 2 grid to navigate. So I can also show this. So what this means is that if the traveler starts from position 1 and moves to the right, so when he moves to the right, he can't go back to the left. So all he has is this 2 or this 3 by 2 grid to navigate. But if he moves bottom to the bottom, then he's going to have he's not going to be able to move upward anymore, so he's going to have the 2 by the 3 grid to navigate. So that's basically what that is saying. So now this is the basic recursion, and this is the recursion with memoization. So on this tree, you can see that if on a 3 by 3 grid, if the traveler moves down, so they have a 2 by 3 grid to navigate, and if they move right, they have a 3 by 2 grid to navigate. So when they are in the 2 by 3 grid, if they move downward again, they have a 1 by 3 grid to navigate, and if they move right, they have a 2 by 2 grid to navigate. On the 1 by 3 grid, if they move downward, that means it's going to be, they don't have they're moving out of the grid, which is not possible. So this is like a base case here. So when you hit 0, it's like a base case. Then when you hit 1.1 1 by 1 grid, when you have 1 by 1 grid left, then that's also a base case. So for example, if you are like, in how many ways can, if you have just one grid, let's say just this grid, how many ways can the traveler move in just this grid? It's just one way. The traveler just has to move one way to be on this grid. Now if you have 0, 1 or 0, 2 or 2, 0, that means it's either the row is 0 or the column is 0, so it's not possible. So if you have row 0, column 2, that's not possible, so it's going to be like a 0. Yeah, so until we hit the base case, the traveler would keep traveling. Then for the recursive function with memoization, like we discussed in part 1, you know that some calculations are already existing. So for memoization, we have to pick out the calculation that has been done before. For example, if we have done the number of ways for the 2 by 3 grid, we don't have to do it again, so we catch it, and next time when we want to do the same thing, we can pull it out from the cache. Another thing to note is that the number of ways to traverse or to navigate through a 2 by 3 grid is the same number of ways to navigate through a 3 by 2 grid. So with the memoization, we can see that when you have a 3 by 3 grid, you have the you calculate for the 2 by 3 grid. Then since you have already gotten the value for the 2 by 3 grid, which is in the cache, you don't have to calculate for 3 by 2 grid, so you have to get that value from the cache. Yeah, so that way you don't have to like repeat the calculation that has been done before. Now you do all the way down until you hit the 0 base case or the 1.1 base case. So looking at this tree, you can say that the time complexity for the basic recursion is going to be 2 raised to power n, which is exponential. 2 raised to power n plus m. N is going to represent the number of columns, and m is going to represent the number of rows. But for a basic recursion, we can say that the time complexity is going to be an O of n plus m. So this is going to be an n plus m time complexity. So now let's jump right into the code and write the recursive function and the one with memoization. So all we basically need to do is just to call the function recursively while passing m minus 1 and n, and also calling the function again, passing m, then n minus 1. So this means that we can actually just move either to the right or to the bottom. So m is going to represent the number of the row. This is the row, and n is the column. So m minus 1 here basically means you're moving downwards, which means that you're reducing the number of the rows, because our m is our row and our n is our column. So, and n minus 1 here means you're moving to the right. It means you're reducing the number of columns that is needed to be traveled or traversed. So this is basically the solution. Then we have to add base cases, which is going to be if m is equal to 1, and also if n is equal to 1, then that means we just have one way to travel. Then another base case we need to handle is if any of them is 0. So that means there is no way, there's nothing to travel, so it's going to be 0, or it's actually invalid. So it's going to be returning 0. So I'm going to do n equals 0, return 0. Yeah. So this is basically the solution to that problem. So if we run this so we can see that our output here is 3. So I want to see in how many ways a traveler can travel on a 3x3 grid and also a 25x25 grid. So I'm going to run this again. So as you can see that the answer for a 2x3 grid is 3, a 3x3 grid is 6, but a 25x25 grid has not returned, and that's because the function is making a lot and lots of recursive calls, and so it hasn't returned. So the solution to this is always memorize. And what do we say about memoization? Which means we're going to catch our results, so that if we have a need to make that call again, we have to first check in the cache and be sure that we have not, or we have it in the cache. If we have it in the cache, then we use the results from the cache. So every other thing would still stand, like this still stands. So basically I'm going to have this code just the same way. Just done integer and the memo objects, which I'm going to represent in a hash map. Oh my god, sorry. So I'm going to do a hash map of string and an integer, which I'm going to call memo. Then I'd have to just call this I'm going to pass the memo object here and also here. Then I'll check in the cache if the memo contains the key, and the key is going to be like m plus n with the comma in it, m plus n, which is going to be a string. Then if it contains it, then please return it first. So we're going to return that the value for that key. So it's going to be memo.get m plus n. Now remember, we also said that if a 2x3 grid and a 3x2 grid would have the same number of ways to travel, so we'll probably want to duplicate this. So we'll probably want to do an n first, then an m, an n first, then an m. So the reason for this is that if, for example, we have in the cache the result for a 2x3 grid, so if we're coming with a 3x2 grid, it's not going to pass this check, because what we have is a 2x3 grid. But if we now reverse it and make the 2 the n and 3 the m, so it's also going to give us the value, the result for the 2x3 grid. Yeah, so that's basically that. Then here we're going to put the value in the memo in the hash map, which is going to be this as the key. Then the recursive function as the value. Then finally we're going to return the last value in the memo object. Okay, so I have this error here. Required type is string. Okay, I didn't use the quotes properly, so I'm going to have it like it's supposed to be double quotes. So this is the solution for the memoized function. So we're going to go ahead to run the long-running task. We're going to call the memoized object, which is going to be this. And I'm just sending objects the same. I'd also want to, test out with this one. Sorry. So I want to also test out to show my memoized function is correct as well. So I'm going to call 3 just like I did in the first case. So I'm going to go ahead to run this. Alright, so we have seen that the solution just returned immediately. This is because we don't have to make a lot of recursive calls anymore since we are catching a lot of results. So that is why memoization is very, very important in recursive functions. So this is the second part of the dynamic programming series, and I'm going to have a third part coming up next in a week or two. And also I got some comments asking for where they can get resources for dynamic programming or questions in dynamic programming. You can also check out LeetCode. There is a section on LeetCode that deals with dynamic programming, and you'd all see a lot of questions and exercises that you can play around with. Thank you for watching. Bye.